So I'm next. I'm Christy Holland, and thanks very much for coming here. I'm delighted to see so many people that braved the weather and came out on a day to see what biomedical engineers do, at least. So the first two talks are from biomedical engineers. And so B is for biomedical engineering. I'm sure you're all curious what in the world I meant by B. And what's fun about today is I get to highlight what my students and postdocs have done. And so it'll be an introduction to the Holland Hive for sure. And in particularly, you might be curious and want to take a closer look. Here's the queen right there. That would be me. And, some of you really might want to take a closer look. This is one of my graduate students' sons. And I want to take a very close look. What's wonderful about bees is they have hairy eyeballs. There's hair all over their bodies. This is a scanning electron micrograph of a honeybee. I also happen to be a beekeeper. And so what is the problem that I want to talk to you today? Well, biomedical engineering has been defined by the Whitaker Foundation. It's a wonderful foundation that has financed the creation of a lot of different biomedical engineering departments across the country. And their definition is it's a discipline that improves human health through cross-disciplinary research. There's the key, cross-disciplinary research, which integrates engineering sciences with biomedical sciences and clinical practice. So what that really means is you never feel quite comfortable, either in the medical school or in engineering. And you have to be rather bold to be halfway in between the two. So what is my point here? What exactly do I mean? That is a bee stinger. What I do is the application of engineering techniques to the understanding of biological systems and to the development of particularly therapeutic technologies and devices. So that's where my focus has been. Okay, back to the hairy eyeball. So what's the difficult problem that I'm trying to solve? And that is stroke. How many of you, raise your hand, if you have a primary family member or a dear one who has suffered a stroke? Let me see a show. Okay, typical, I'm seeing about 40% of the room. This is a huge problem, cardiovascular disease. Many, many people are stricken by this terrible disease. And what happens with this disease is a blood clot. These are fibrin strands, erythrocytes, those are red blood cells. So a blood clot gets caught in the vasculature of your brain, specifically usually in the middle cerebral artery. And these are the two major arteries that essentially serve the left and right hemispheres of your brain. So just since I had the opportunity, I want to do a little stroke teaching here. The signs of stroke: face, if you see a face, if it looks droopy or uneven; arm drift, if you have paralysis on one half of the body; or speech, if that person doesn't make sense, perhaps hopefully not me today. Does their speech sound strange? Then it is time to call 911 immediately, because brain is time. You have 3 hours to save that part of the infarcted brain. So what I have done with my lab is come up with technology. It's a transducer that helps work a drug called tissue plasminogen activator, or TPA. It's a clot-busting drug. Essentially try to clear that part of the neurovasculature which has been blocked by a blood clot. And you have to race time, otherwise you die rather rapidly, or that part of the infarcted brain dies. And what we've learned is that you get better breakup. That drug, that clot-busting drug, TPA, works better if you have a little bubble activity. Imagine that. So we've got lots of publications that have shown us that if we have a certain kind of bubble activity, it's called stable cavitation. So this nice, friendly, gentle bubble activity, kind of think of it as singing bubbles, then that helps this drug work better, as opposed to kind of a bubble collapse or inertial cavitation some of you might be familiar with in the audience. So if I hit a bubble that's pre-existing with a sound wave, let's say at 120 kilohertz, that's above what we can all hear, then that bubble will sing. And it will sing at a particular amplitude, half the fundamental. So if I'm hitting that bubble with 120 kilohertz, it will sing at 60 kilohertz, if it's just right. This is the kind of singing bubble that we try to promote, as opposed to inertial cavity, where if we hit it and it grows and it just collapses violently. That can do a lot of damage. In fact, there's submarine propellers. If any of you are boaters out there, you'll see cavitation damage on the marine propellers. That's a more violent kind of cavitation, and we try to avoid that, particularly if it's in your brain. And what the wonderful students and postdocs that are in the back have done is they've discovered that if we have an kind of an interval on and off period, so there's an on period, the ultrasound is on, where we get this nice bubble activity, And then after that bubble activity dies out and it's no longer nice, you might as well turn the sound off and let the bubbles come back in down the bloodstream. So we have on and off. And that's what we've done. And I'll show you some pictures of that. So what's the bee's knees in my lab? The bee's knees. The coolest thing out of the lab, I think, is we're developing nanoparticles that are liposomes, and they happen to be echogenic. So they work very well as an echo contrast agent on an ultrasound image. That's because of this little gas bubble that's trapped within a lipid monolayer. The whole thing is surrounded by a lipid bilayer, just like Carla said, membranes. Baby membranes are where it is. So this is not unlike a red blood cell, except for there's not much inside other than a drug. We can put that drug TPA on the inside of it. Okay, now that means I can follow on an ultrasound image where that drug goes through the vessels in your body. Not only that, but I could coat the outside of this liposome with targeting agents that would maybe make it stick to clot. And that's what we've done, is we've created these echogenic liposomes, and we've used different molecular Velcro strategies in order to get them to stick to things, particularly to clot. There are a number of different strategies that people are using, including Bracco in Switzerland. They're kind of trying to target a receptor that has to do with clotting, GP2B3A receptor. Or there's a linkage that targets fibrin. That's a group at Washington University that are doing that. And then our group down in Texas and here are using inactivated TPA. So we're taking that drug that's made by Genentech. Yes, we're taking on Genentech. And we are cleaving it in half and using half of that drug to target the clot. And we put on the inside of that nanobubble in that liposome, that tiny liposome, the drug. So now we have a clot-seeking, image-guided, ultrasound-triggered clot buster. And this is kind of the concept of how it would work. You would inject it into the veins in your body, and you would only release it at the site. TPA is a pretty nasty drug. It can cause lots of side effects and hemorrhaging. And so if we can only focus it right where we need it, it would be better. And that's what we do, and this would be a close-up look. So only where the beam of ultrasound crosses do we pop that bubble and deliver the drug. Here's an image, a transmission electron micrograph of these nanoparticles. So you can see there's a lipid bilayer, and every once in a while you can catch a little air bubble in there, surrounded by a monolayer. So they're very broad size range. They're all the way from 70 nanometers up to maybe 6 to 7 microns. So it's a broad range of sizes, and that means they scatter sound at both intravascular ultrasound frequencies as well as transvascular ultrasound or transabdominal ultrasound frequencies. So how do we gather data? The pollen basket of the honeybee. We gather data by using techniques both in vitro, ex vivo, and in vivo. So both living and non, and this happens to be an in vitro system, so it's not living. The clot itself is living. We've caught a clot, human blood clot, on a suture, a silk suture, under a microscope. Now I'm going to show you how these encapsulated TPA works on the left versus if I add a little ultrasound on the right. I'm going to try to race it so you can tell me which one wins. Okay, so once again, these TLIP or TPA encapsulated liposomes on the left, there's some TPA on the outside and as well as some endogenous TPA in the plasma. This one wins. So just by adding a little ultrasound, if I have a stroke, give me that, please. I'd prefer that one on the right. And recently, another student in the lab has added flow around that clot, so it's a little bit more like the body. And you can see we're doing automated image detection, edge detection, so we can follow exactly what that size of the clot is as a function of time. And it just peels right off. I want that one, please. This is with TPA. This is with only plasma. That means this person's having a hard time getting rid of that clot. That one's doing pretty well, though, with TPA. In fact, what you're left with at the end is just the silk suture. And so we can use that to compare therapies or to compare drugs or to compare different kinds of ultrasound parameters. And that's the sort of systems that my lab uses to study. Now, you might ask, yeah, but what happens, what goes downstream when you're done? Another student has looked very carefully what's blown downstream, and it's very tiny, nothing larger than a red blood cell. So it's just really wonderfully simple, and it works. It is patented. And that, in the end, is how you end up with living things. The beehive, you're right in the middle of it. So I would like to acknowledge funding from NIH and all the wonderful collaborators I have. Chip Shaw is in emergency medicine. Joe Broderick is in neurology. Gail Pine-Geitman in neurosurgery. David McPherson is down at UT Health Science Center. He's an internal medicine cardiologist. And then, of course, students and postdocs on the ultrasound enhanced thrombolysis project is Nick Ivancevich. Kate, Steve, Jay, and Matt, they're all working on that project. And then echogenic liposomes are being developed by Kevin Hayworth as a postdoc. Jonathan Kopacek, Kirti, Jason, everyone, thank you so much. And at the end, you get honey.